chat about some stuff here. Chapter 13 was all about looking at acids by themselves or bases by themselves. This chapter is going to look at acids and bases together. So, we're going to look at acid-base reactions in this chapter. And a lot of the same stuff from chapter 13 is going to play a role here. But, and a lot of times we talk about them as being neutralizations. An acid plus a base is a neutralization. But I put that in quotes because an acid plus a base, even when you completely react all the acid with all the base, isn't necessarily neutral. So we're going to talk about that today. A couple of things I want to talk to you about today. I want to talk to you about a couple of different acid-base reactions. And I want to talk to you about indicators, which are, this is the chapter where, you remember in Chem 1, doing titrations, right? Colorless to pink. You remember that? Okay, a couple of you do. The rest of you, like John, is still asleep. You can't. Okay. All right. So let's take a look at these, and we're going to kind of add some things as we go. First thing we need to know before I look at a very specific thing is that we need to know that these reactions go to completion. So these are not ones that are equilibrium like we were talking about in chapter 13. The actual reaction between an acid and a base goes to completion. So we're going to look at three different ones. We're going to look at a strong acid, strong base reaction. And I'll just kind of give you some examples. So an example of that might be nitric acid plus sodium hydroxide yielding NaNO3 and water. If all of the acid and all of the base get totally used up, what will the pH be like at the end of this? Rajan? It's going to be neutral, 7. Why? How do you know? It's just going to be water. What about this? Salt. Mark? They don't react with the water because Na plus comes from a strong base and NO3 comes from a strong acid. There's not going to be an affinity for that hydrogen and water. And so this is going to be a neutral solution at the equivalence point. So here's a vocabulary word that we need to address, equivalence point. Equivalence point is the point where the acid and the base are exactly neutralized. Again, I'm using this word neutralized very loosely because it isn't always going to refer to being neutral. But when the acid and the base are entirely reacted with each other and there's no more acid or base left in that solution, it's only products, that's the equivalence point. And so the equivalence point for this reaction is going to be neutral. It's going to be a pH of 7. Another vocabulary term that we need to know, endpoint. The endpoint is what we consider in a titration. This is when the solution changes color. And so, thinking about a titration, you've got like a little burette and your Erlenmeyer flask. We'll do one of these later this week. And, let's say you put your acid in there and your base in the burette, and you put your indicator, like phenolphthalein, and what you want, if you're trying to figure out, say, the concentration of, say, the acid, you want to know when the equivalence point is. But the way that you can tell that is by putting an indicator in and seeing when it changes color. And in the case of phenolphthalein, it's either pink or colorless. When is it pink? Under what conditions is phenolphthalein pink? Eric? Basic. When it's basic. And so what you want is, you add a final drop of base, which turns it basic, and it turns pink. You want to have the equivalence point and the end point to be as close to each other as possible. So there may be like 1 drop difference. So you'd like it to change color as close to the equivalence point as you can. That's your goal in a titration, is for that to happen. Okay? So that's a strong acid, strong base. Let's take a look at another type of acid-base reaction. Let's take a look at a weak acid, strong base reaction. So perhaps we do HF and sodium hydroxide, because that's a weak acid. What are the products of that reaction? Rajan? Right, water and sodium fluoride. This one is not neutral at the equivalence point. Why not? Why is it not neutral at the equivalence point? Matt?
Not all the HF associates.
Well, all the HF will be used up at the equivalence point. There actually won't be any HF or NaOH in there, because that's what the equivalence point means. Sagar? Right, because this is not a neutral salt. So when that goes to completion, we still actually have an equilibrium that's going to impact it. In that NaF, we've got F minus, and that F minus is going to react with water. Now this one is equilibrium. What are the products of that? OH minus and HF. And so as a result, this kind of a acid-base reaction is actually basic at the equivalence point. And so its pH would be greater than 7 when you hit the equivalence point. When you've completely reacted all the acid and base together, it actually will be a basic solution. We can do the opposite of that. We could do a strong acid and a weak base. So like HCl and ammonia. So Alden, what would be the products of this reaction? Let's give this a little plus because of the H plus, right? So NH4 plus and Cl minus, this one, when you hit the equivalence point, is also not going to be neutral. Why? What part of those products is going to make that solution not neutral? Which one? The NH4 plus. And so NH4 plus, you can react it with water. Now this is equilibrium, this salt reacting with water. Maddie, what would the products be? Exactly right. NH3 and H3O plus. And so because of this, that's going to be acidic at the equivalence point. Whoa, I cannot write. Ooh. And so the pH is going to be less than 7 when you hit the equivalence point for this titration. All right, certainly you guys, we could do a weak acid, weak base one, and that can exist and neutralize each other, but we're not going to be doing any mathematics with those at all. In fact, your book doesn't even talk about those kind of reactions because it involves multiple equilibria overlapping, and so we won't be calculating that, so I'm going to just leave that. It's not that it can't happen, it can. It's just we're not going to be covering that. Here's what we need to do, though. In order to actually do a reaction like this, you need to know when you hit the equivalence point. How do you know? Because you use an indicator who gives you an endpoint really close to the equivalence point. So what we need to do is to talk about indicators now for a second. So we can understand how they work and how we know what color it'll be and the various pH, things like that. And so here's what we need to know about indicators. Indicators in general are usually weak acids that have a color to them. And usually its conjugate base has a different color related to that. Hi, Ankit. Thank you. All right, so we're going to, in general, call indicators, since they're weak acids, instead of calling it like HX or HY, we're going to call it HIN. I don't mean IN as in indium. I mean IN as in a generic indicator, part of that. So if, for example, we're talking about phenolphthalein, in the case of phenolphthalein, it could be found in the form of HIN. There's an equilibrium because it's a weak acid. Also, that's shaking. The HIN version is colorless. So when we have a large concentration of the acid part of that equilibrium, we see colorless. The IN minus is pink. And so when we see a solution that's pink, that means there's a lot more IN minus than HIN. And we see a solution that appears colorless, there must be a lot more HIN and very little IN minus. And so that's how our eyes will perceive that. So let's do like an example, not using phenolphthalein, using a different indicator. And let's write the equilibrium associated with this indicator. And I'm making this indicator up. So I'm going to say that when it's in the HIN version, it's red. And when it's in the IN minus version, it's blue. And it's a weak acid, so I'm going to give you the Ka as 1 times 10 to the minus 8. So we're just going to kind of see how these indicators work. So if I write the K expression here, looks like that. And I'm going to go ahead and rearrange it a little bit. And I'm going to divide both sides by the hydrogen ion, just to serve a purpose here. Here's what I want to look at. We're going to do a problem first. And here's the problem associated with this. I want to know what color will this indicator be if added to a solution with a pH that's equal to 1. All right, first of all, taking a look at the reaction itself, what would your guess be? What color would you expect it to be if it's added to a pH solution of a pH of 1? Sagar? Red. Why? Yeah, so if you have a high concentration of hydrogen ions, it's going to end up causing it really essentially to shift left, which would cause you to have more reds. Now we're going to look at it mathematically as well. So using this reaction right here, if we plug in what we've got, we know our Ka is 1 times 10 to the minus 8, because I gave that to you, divided by the hydrogen ion concentration. What's the hydrogen ion concentration? Yep, not quite. Oh, yeah, times 10 to the minus 7, sorry. No, it's not times 10 to the minus 7. Yes, times 10 to the minus 1. Is equal to the IN minus over HIN. You computed the difference already, right? Which, if I'm going to just put that in fractional form, I don't always like to look at fractional form, but it'll help me make my point. You know, 1 times 10 to the minus 8 divided by 1 times 10 to the minus 1, that is essentially the same as, make sure I got my zeros right, 1, 2, 3, 4, 5, okay, 1 over 10 million. That's the difference in their concentrations. So, when we look at that, we've got an awful lot more HIN than we do IN minus. So of course, it appears red. Now, what if the ion minus and the HIN minus, or the ion minus and the HIN concentrations were similar? What would we see? Purple, right? And so that would be our equivalence point, would be purple, which is a difficult one to tell because when's purple? Is it red purple? Is it blue purple? Is it purple blue? Kind of hard to tell when it's actually purple, but the true equivalence point would be purple. So let's think about how do we choose the right indicator? Okay, so we're going back to this. All right, when you hit at the equivalence point, what we want to be true is we would, at the equivalence point of our titration, we would like to have the HI and the ion minus concentrations be the same, like purple. Same concentrations of red and blue. We want that to be true at the equivalence point. So we want the concentration of HIN to be equal to the concentration of ion minus. That's what we want for our indicator. We want it to change color at that point. So that would be the kind of switchover point from one to the other. If that's true, and we know that Ka over H plus is equal to ion minus over HIN, if these guys are equal, then what's true about these? Those are equal. And so we know that the Ka is equal to the H plus. If we take the negative log of both sides, then the pKa, negative log of the Ka, would just be called pKa, is equal to the pH. This pH is the pH at which you want the color to change. So when you're picking an indicator, if the equivalence point is going to happen at a pH of 3, then you're going to choose an indicator who has a pKa of around 3, or a Ka of 1 times 10 to the minus 3. So let's take a look at some indicators. This is a chart that lists, I don't know how many, 50 different indicators. And it also lists the pKa, their pKa, or their pH at which they change color. And they run anywhere from up here at the top, this is methyl violet, who has a pKa of about 0.8, which means it will change color at a pH of 0.8, from yellow to blue. So at the equivalence point is green. Down to, we can take a look at, let's say, methyl red, which is a fairly common indicator, which I just lost. Oh, there it is. Methyl red has a pKa of about 5, so it changes in pH 5 from colorless to red. Bromothymol blue has a pKa of, looks like about 6.5. Changes from, no, actually we're closer to 7. Yellow to blue. Phenolphthalein has a pKa of about 9. This means it changes at a pH of 9. Which might strike you funny because we always use it in our acid-base reactions, but yet its pH doesn't change to 9. So we need to talk about why that would still be an okay indicator. And there's a couple of things. You want, when you choose an indicator, you want this pKa to be changing around the pH. But you also need to choose one that's going to be easy to tell the equivalence point. Because in the case of bromothymol blue, which is yellow to blue, what color is it at the equivalence point? Green. It's really difficult to know what's the right green to stop the titration? Because it goes from yellow to yellow-green to greenish yellow to green blue to blue-green to blue. When is it green? You're trying to make that judgment. That's hard. Like phenolphthalein, it's colorless or it's pink. That's an easier decision to make. And so that's also a role that you have to decide, which indicator am I going to use? Methyl red, which I mentioned, is one that they like to use because it's another colorless to red one. It's a lot easier to make that decision. So we're going to be talking about indicators as we go through this chapter quite a bit. And we're going to be looking at some of these ideas and how do you know which indicator should I choose for this titration or that one. Okay? Questions? All right, so now you've got a job. Okay. So we have this problem. And let me talk it through and I'm going to give you time to copy it down. Here's what you're going to be doing. And we're going to be looking at a variety of titrations as we go. But you're going to do this right in your notebook. I want you to compute the pH of this titration kind of along the way as it goes. So you're starting with 50 milliliters of acid, of 1 molar acid in the container. And these along the side are how much titrant, the base, sodium hydroxide you're adding. And I'm giving you the concentration of that. And what I want you to do is I would like you, for these 6 points, is I want you to compute the pH. So for part A, I want you to compute the pH of just the acid before you've added any base. That's a simple computation. And then for part B, you're adding some base, but not enough to actually react all the acid. So this is a limiting and excess reactant problem. Think Captain Kirk from last week. My recommendation to you as you compute these is to consider using moles. And the reason is because when you're doing a limiting and excess reactant problem, if you can compute the number of moles, you might even want to do a little ice table if it helps you to see it. You don't have to. You've got a certain number of moles of HCl and you're going to add a certain number of moles of NaOH and it'll help you to see who's limiting in excess and therefore how much is left in the end. But at the same time, as soon as you add some base, you no longer have 50 milliliters here. You now have, like in part B, 75 milliliters. So if you do it in moles, you can now divide it by the new volume in order to help you to compute the pH. So that's my recommendation. I want you to go through each one of these along the way, and then I want you to graph the titration curve. Just in your notebook, I want you to do a quick sketch, essentially of pH versus the milliliters of the NaOH added, and just do a little sketch for me. You should be able to finish this in here. You will, because you guys have enough time to do that. While you're working, I'm going to pass out that worksheet to you. So if you finish it and you're waiting on other people, go ahead and work on 1 through 5 on the worksheet. But I'm going to leave this up. I want you to copy it down, and then I want you to compute it right now in class.